Hi, good morning, everyone. Reminder this afternoon, recitation is help for the project. So if you're still working on the project and you have some questions, please make sure to ask. Okay, so we took a look at this problem, and we had to kind of blow through the very end of this kind of quickly to get to the main point. So I want to revisit this very quickly. So we took a look at going through the example. We had this open loop transfer function, and then we plotted the Nyquist plot for this example. And so we had, in this case, because we had a pole at the origin, we had an issue where we had to have a infinite loop in this contour of our Nyquist plot. So it took a little work trying to evaluate, does this loop close in the left half plane and the right half plane? We determined that it closes in the right half plane. It doesn't always close in the right half plane. So if you look at the sheet that's being passed around, there's an example, the middle one, where the Nyquist plot closes in the left half plane. So anyhow, we were looking at this and we said, okay, is this system stable the way we drew this Nyquist plot? And we looked at the number of poles in the open loop system in the right half plane. That was 0, because if you look at the transfer function, we have no poles in the right half plane of the open loop system. And then we looked at encirclements, the point -1, and we looked at this Nyquist plot. We said, okay, this plot does not encircle the point -1, right? And so by combining these two together, we can determine, for this example, this is our equation we did on Monday, that this is stable closed loop system. So Z, remember, is the number of poles of the closed loop system in the right half plane. And then we did, quickly before we had to go, we did this little thought experiment. Said, okay, what happens if we were to increase K, the gain of our open loop system? What's going to happen, right? And so we said, all right, from what we talked about on Monday, if we increase K, this essentially dilates the Nyquist plot. So it just expands it, scales it about the origin. So if I were to do that, all right, so the areas at infinity are still at infinity. That doesn't really change. All right, so now my plot is scaled. And so if I increase the gain large enough, it's going to now encircle -1. All right, if we look at the number of encirclements, so just to note, this is K greater than some K critical. All right, it's going to encircle the point -1. And so now when we evaluate whether or not the system is stable, we would get that there are 2 clockwise encirclements of the point -1. So that in terms of the number of counterclockwise encirclements, that's -2. And so we would get that we have 2 closed loop poles in the right half plane. So that was just a recap of Monday, right? So this is what it looked like for a larger gain. So tying everything together here, for this system, if we were to look at a transfer function that looks very much like this, I'm just making up a transfer function right now as we go along. So if we have G is equal to, that would do ZPK. Then we have poles at 0. Actually, let me do it this way. All right, so this would be a transfer function that looks a lot like what we're studying right now. Second order underdamped with an extra pole at the origin. If we were to look at the root locus for this system, right, we would see the same result. So we get actually complementary information. So here we have no poles in the right half plane for small gain. Then we have a transition from 0 poles in the right half plane to 2. the right half plane for larger gains. Right? And so we can see this in the Nyquist plot too, is that as our gain gets larger, we go from having 0, this is small gain, right, close to the open loop poles, that we have 0 poles in the right half plane, but as soon as it gets across some threshold, now we have 2, right? So there's a direct transition from going 0 poles in the right half plane to 2 poles in the right half plane. And then this is reflected in the Nyquist plot as well. So same information, so different ways of analyzing this, but same result, right, which is what we'd expect. If we had different answers to these, we would have to be suspicious of our work, right? Any questions on that thought? In front of you, we have a handout. So I'm going to go through that handout. Okay. So this is what you should see in front of you. So on the left here, we have the locations of the open loop system poles and zeros. So each of these is a pair, right? So these are, on the left column is the pole and zero locations for the system, and the right is the corresponding Nyquist plot for that system. So for each of these, we're going to just ask the question, is the system stable? Okay. So this one looks almost, this is essentially what we've already done before. So I'll go through this one quickly. So if we look at, if we're trying to say, all right, is this system stable? We're looking at this equation. Z is equal to P minus N. So P is the number of poles of the open loop system that are in the right half plane. N are the number of counterclockwise encirclements of the point -1. So if we look for this particular example, we have 0 poles in the right half plane, and we have no encirclements of the point -1, right? So this Nyquist plot never even gets close to -1, right? So this would be 0 minus 0 is equal to 0, and then our result here would be that this is stable. So this is easy. This is a lot like what we did for one of the examples. Example 1, I believe. Okay, how about this one? Is this system stable? What do we think? No, okay. So why do we say no? Okay. Okay. So adding these up, right? We have one way to consider the number of poles in the right half plane of the open loop system, right? So if we do Z is equal to P minus N, right? So we have 1 pole in the right half plane. It's right here in the open loop system. So the open loop system is definitely unstable, right? Because we have a pole in the right half plane. We're asking the question about the closed loop system. So we have 1 pole in the right half plane, minus then the number of counterclockwise encirclements of the point -1. And so Tyler's saying that here we do not have a counterclockwise encirclement. We actually have a clockwise encirclement of the point -1. So that would give us -1. So this would be then 2. So this would be unstable. Right? So here we have 2 poles in the right half plane for this system. So any questions on this one? Is this a little bit more difficult? Okay. So going back to the first one, what happens if I were to increase the gain on the system for the first example? Is that going to change the stability of my system? All right, so I see a lot of heads shaking no. Why is that the case? Yeah. So if we were to increase the gain, trying to kind of track this a little bit, the shape would look like this. This would be k greater than 1, right? But this contour is still not going to encircle the point -1, right? And that's because the phase angle of g of s never goes past 180, or -180 for the open loop system. Okay, what about the stability of the second case if I increase the gain? What's going to happen if I increase the gain by a sufficient amount? Karsten. Exactly. So if we look at following the arrows here, the arrows are given. All right, so Carson is saying is that if I increase the gain for the second system to a sufficient amount, I'm going to get this contour. Oops. Okay, so this is going to be our directions of our contour. Okay, so now if we look at stability for the case of k greater than some k critical. Okay, so what is p in this example where I've increased the gain? Still 1. I haven't changed it, right? So I haven't changed the open loop system poles at all. So minus then the number of counterclockwise encirclements of the point -1. So now we see that we have 1 counterclockwise encirclement of the point -1. So now the system becomes stable. Okay, so then try to tie this to the root locus plot. First example, root locus plot would look like this. Right, so no matter what the gain is, these lines are never going to go into the right half plane. So the system is always stable regardless of gain. So that everything jives there, right? Everything makes sense. Now look at the root locus plot for this system. I have 1 more pole than 0. So I'm going to have a single asymptote, which is at 180 degrees. And this would be the root locus on the real axis. Right? And so we know that we have 2 branches here. These have to break away. One has to go to the asymptote at -180. The other one has to go to the 0. All right, so I'm going to have very rough drawing, but this is going to be the root locus plot. Okay, so what this is showing is the same information, right? So we said for low gain, we have 2 poles in the right half plane. That's given by low gain here, which is closed loop poles along this branch. As my gain goes larger and larger, it's going to then get to a certain point at which now the gain gets large enough that I push both of those poles simultaneously into the left half plane and become stable again, or become stable. Okay, so you see how, just want to pause here. Does everyone see how these 2 pieces of information match? All right, now for the tricky one. Okay, is this, yes, Dan? Yeah, let me remove this. I circled this pole, which makes it look like it's part of the root locus. It's not. So for small gain, the closed loop poles are close to the open loop poles, right? And as I increase my gain, these closed loop poles along this branch are going to march in this direction. and this one is going to go in this direction as gain increases. So both of these poles are going to be in the right half plane, unstable, and then as I increase the gain even more, it's going to break away from the real axis and then follow this path until it gets to be so large it's now in the left half plane. So it goes to being stable. So low gain, the system's unstable. High gain, the system is stable. Okay. All right, last example. Is this system stable? All right, so we have, the easy part is figure out the number of open loop holes in the right half plane. That's 0, right? All right, so these are 2 poles at the origin, right? So anytime we see this hashtag mark or check mark, that means you have a double pole. These are at the origin. These are not in the right half plane. Okay. These are really close, but not in the right half plane. And so the question is, how many encirclements of the point -1 do we have here? Should be 0. I agree. Why is it 0? It doesn't. At first glance, it doesn't look like 0, right? Okay. Yeah. All right. So yeah, these are a little tough to see. Here's my only rule of thumb for helping out in this is I find it effective. Say, okay, if we look at this is the direction at the infinite loop. So you can just go from left to right and count the number of loops going up and loops going down, and that gives you a sense of it. So if I'm going from left to right here, I go 2 up, right? And then as I get to this point, I have 2 down, and those essentially cancel each other out. And so we have 0 encirclements because we had 2 clockwise, 2 counterclockwise encirclements of that point. So that's the easiest way. Just look at the number of line crossings as you go from left to right. Yes?
Should you not just do like it's going to be counterclockwise inside where that dot's at, and then the larger one's just going to be clockwise and just cancel out?
Yeah, that's another way to look at it. Yeah, but then you have to kind of see where all these are, and so you can also just do the number of line crossings as well. Yeah, I agree. There are multiple ways to look at this. So yeah, so you're saying this one is in a 2 counterclockwise loops, right? And then this one is in a single counterclockwise loop, and this one's in a clockwise loop, right? And so they cancel. Or the outer one's a clockwise loop. Yeah. Okay. But yeah, this one's a little bit more difficult to look at, but yeah, this is a stable system. Okay. All right. So then the question is, what happens if I increase my gain? So let me erase all this. All right, so this is k is equal to 1. All right, k greater than some k critical. So it means I'm increasing the gain such that I've dilated the Nyquist plot, so now -1 is inside this loop. Is the system stable or not? Unstable. Okay, so why is that? 2 clockwise encirclements. So following this around. Exactly. So if we look at then this case, so we're going to increase the gain to a certain amount. Now the point -1 is going to be inside this loop. This is going to be 2 clockwise encirclements. So this is going to be unstable. And then the last case, k less than some, we'll call this k critical 1, k critical 2, such that now I've shrunk the Nyquist plot so much that -1 is now in this location. Stable or unstable then? unstable. All right, so if we look at this case, we have, you can think of this as 2 up, right? Or just 2 clockwise encirclements. So I have this encirclement, and I have the outer encirclement as well. Okay, so this is a case where it's stable in some happy medium of gain, and if the gain is too small, it's unstable. If the gain is too large, it's unstable. Okay. Any questions on this handout? Any other questions about this? Yes? 2 and not what? So for so this case we're saying for k less than some value, right? So okay, greater than. Okay. So we have, if we look at this case, this is now we have, this is where, if we say, I can't, it's easier for me to move around the point -1 than to expand or contract this, right? So if we look at this, this is under an outer loop, right? Which is, it's the outer loop, which is clockwise, right? It's not in this inner loop, though, right? Right? Which is the counterclockwise one. And then it's under another clockwise loop right here. So we have outer loop clockwise, inner loop clockwise. So we have 2 clockwise encirclements. Yes?
So, the third example, is that not something you'd expect us to be drawn by hand?
No. This would be a little tough. Yeah. This is a little bit beyond what you have to be very good to do this. Yeah.
So, just conceptually, Nyquist plot is another method to determine stability.
Yeah, this far until about 5 minutes from now, we'll talk about it differently. Yeah. Yeah. As you may want to, I think everyone's asking, okay, we can see this information on the root locus plot. Why do we care? Right? Okay.
Yeah.
That's what is in everyone's mind right now. Every single person. Okay. Great. let's address this issue then. Okay, so gain margin and phase margin. All right, so this is a reason why we may care about complementary methods beyond the root locus plot to try and determine stability. So I talked about this a little bit in previous classes, but we have factors of safety in control systems as well. So just like you have it for building a truss structure for a bridge, in terms of factor of safety, we have it for control systems. And this is coming from the fact that, well, one, our controller, we can usually, if this isn't some sort of microcontroller system and you have a really good microcontroller, it's going to behave pretty much exactly as you designed it, right? In terms of the differential equation that is being output of the system. But the plant is always going to be an approximation of the actual plant dynamics, right? So you have a model of some sort of physical system. Your model is not going to be perfect. And so you have some uncertainty in what your plant dynamics actually are. And so just like if you're building a truss structure for a bridge, you have some uncertainty in what the actual, say, yield strength of that material is, right? It may be specified to be something, but there could be porosity in the material or some other factor, right? So same idea here. We never know perfectly what our plant model exactly is, and so it's good to have factors of safety for this. And that is what we're going to call the gain margin and phase margin for the system. So the gain margin, the typed out notes has the book's definition. I don't find the book's definition to be very helpful. So we'll go with my definition of this. So the gain margin so GM is the gain margin, is the difference or distance, distance between, I put a space here because I want to draw this in. Actually, this is the equation, so I want to write this out. All right, the distance between G of I omega expressed in decibels and 0 dB at the frequency at which the phase is equal to negative 180 degrees. Okay, so keep in mind, when we were looking at the very beginning of this lecture, we talked about this marginal stability point, and that was the case where we simultaneously have a phase angle of negative 180 degrees and a magnitude of 0 decibels. Right? And so that's the point we care about in terms of marginal stability. And so now, if we want to know what's called the gain margin, we're now looking at distances away from instability. Okay, so this is maybe a little bit tough to digest at first. We're going to go through some examples to show this case, but this would be the definition of gain margin, phase margin. This is, I didn't write this out actually, I probably should have, gain margin. Phase margin. The amount by which the phase of G of I omega exceeds negative 180 at the frequency at which the magnitude of G of I omega is equal to 1, or magnitude of G of I omega expressed in decibels is equal to 0 decibels. Again, same basic information in terms of we're looking at distance from this marginal stability point, where instead of looking at gain, which is what the gain margin is, we're looking at in terms of phase. Okay, so the reason why we look at this in terms of phase as well is because a system, we say a plant, if we describe in the frequency domain, has magnitude information and phase information, right? That's what's in the Bode plot. And you can be off in magnitude and perfect in phase, and you can be perfect in magnitude and off in phase. Did I just say the same thing twice? What did I say? You can be on in terms of perfect matching of your magnitude, but be off on phase. And you can be perfect in terms of your phase information and off in magnitude, and you can also be off on both, right? And so we're looking at trying to understand how close we are to instability in terms of both magnitude and phase or given system. All right, last definition that it's not really fundamental to this, but it's somewhat similar, is what's called the crossover frequency. This is omega c, is frequency at which magnitude of gi omega is equal to 1, or magnitude of gi omega in decibels is equal to 0. Okay, so I think these are kind of difficult to look at or understand at first glance, so we're going to do an example to help explain this one. Okay, so example 15.3, find the gain margin and phase margin for this open loop system. And so what we have here is just a system with a gain of 4, and then we have 3 poles, and the poles are at -2, -10, -20. So pretty basic. Transfer function here. So if we were to look at the Bode plot for the system, this is just to be kind of roughly drawn. We have so we have a gain of 4, which puts us above 0 decibels for a certain period, and then we're going to have a few frequencies of interest. Okay, frequency of 2, frequency of 20, or sorry, 10, and then a frequency of 20. All right, so we're going to have 0 dB per decade slope until the point of 2. Then we're going to have a decrease in -20 dB per decade from the first pole, -40 from the second pole, and then -60. All right, from these 3 different poles. Phase, we're going to get -90 from each of these. So you're going to have -90, -180, -270. Just kind of roughing this in, this is basically going to transition from 0 phase to -270 over the span of these pole locations. Okay. Any questions on that? So if we look at the Nyquist plot for this, and just pull off some frequencies of interest, let's pick out this frequency here. We'll call this omega A. All right. Another one that's good to pick out is going to be actually the frequency at which we cross 0 decibels. Right, and we call this the crossover frequency. Sorry, I want to do that to be omega A. All right, I'll call this omega C because that's the crossover frequency. So that's when we know exactly the magnitude is exactly equal to 1. Then after that, it's just going to, this will be a fairly uninteresting Nyquist plot, but it'll be instructive for helping us understand gain margin and phase margin. And so this we'll call just omega D. So we skipped omega B, but that's okay. All right, so we have the first frequency omega A, crossover frequency omega C, and then omega D. So if we look at the very first one, at really low frequencies, we know that we have a magnitude of 4, because that we can actually take that just from this transfer function All right, so very low frequency, just think of all your s's are equal to 0. Magnitude of 4, and this is going to be approximately a 0 degree phase. It's showing it just slightly less than 0, but for all intents and purposes, where we're starting at here is we're starting at 4, and that would be this very first segment, a vector with a 0 phase, magnitude of 4. I'm going to draw the unit disk on this because that's going to be important for us to understand the system in terms of gain margin, phase margin. So this would be a disk with radius 1. Right. And so as we go up in frequency, our magnitude is going to decrease and our phase is going to decrease. Right. So the vectors that we're drawing here are going to start to have smaller length and then smaller angle. If we measure this as negative angles going in the clockwise direction from the positive axis. Right. And then eventually we're going to get to omega c, right, which has a magnitude of 1. And here we're showing approximately, to the best of my drawing abilities, a phase angle of around negative 90 degrees. For purposes of instruction, let's just make this a little bit less than negative 90. But we're basically having a Nyquist plot, which is winding around in the clockwise direction, getting smaller in magnitude, crossing a magnitude of 1 at this omega c. So this would be G. So this would be G evaluated at the crossover frequency is exactly when it's equals to magnitude of 1. And then if we look at how this finishes, it finishes with a very small gain and a phase angle of negative 270. Right, so negative 270 is also a positive 90, right? So that's due north. So it finishes like this. Let me make sure these connect correctly. Oh, crap. All right, let's undo. All right, so this is the first half of the Nyquist plot. Okay. Any questions about the correspondence between the Bode plot and this Nyquist plot? In this very rough approximation. Okay. Dan.
How did we initially determine what's moving clockwise?
Okay. So yes, this is to add on to that. So this is increasing frequency. All right, so if we look at this, we have phase information that's continually decreasing. All right, so as we go up in frequency, the phase only gets smaller. All right, and so that's going to be corresponding to negative angles, so that's a clockwise rotation. All right, so finishing the negative frequencies, that's just reflecting this about the real axis. And this is the finished Nyquist plot. Yes?
Can you explain the omega c part again?
Yeah, okay. So omega c is a crossover frequency. That's the frequency at which the magnitude is equal to 0 decibels. So that would be, on the Bode plot, that's where the magnitude plot crosses 0 decibels. And that's also equivalent to a magnitude of 1. Right. And so that would be then a case where g of I omega is a vector, and the vector has magnitude 1. Right? So that would be this vector here with magnitude 1, or also where it intersects the unit disk. Okay. that make sense? Okay. Okay, so this is then the Nyquist plot for this example. And now we want to understand what is the gain margin and phase margin for this system. Right? So one, note the system is stable, right? So we have all poles in the left half plane, and this does not encircle the point -1. Right? Now, if I were to increase the gain enough, this would actually become unstable. So if we increase the gain a lot, we're going to go from having 0 counterclockwise encirclements to 2 clockwise encirclements. And you're going to go from having 0 right half plane closure poles to 2, right? And that gain increases. So that's the first thing to note. But if we look at this definitions for gain margin, so Gm is the distance between G of I omega in decibels at the frequency at which the phase is equal to negative 180 degrees. So the easiest way to see this is actually on the Bodhi plot, and we're gonna draw these on both so you can kind of see the correspondence between them. But we're saying, all right, let's look at the frequency at which the phase is equal to negative 180 degrees. So drawing this here, this is negative 180 degrees, right? And so this corresponds to that frequency, right? So if I look at this frequency, I would then go up to match this up with the magnitude plot, but this is the frequency at which this happens, right? Frequency at which the phase plot crosses negative 180. This is the gain margin is the distance between 0 decibels and the magnitude at this frequency. So the gain margin would be just a distance on your Bodhi plot, and this would be the gain margin for the system. Right, so we don't have units on this or anything, but we could measure this directly off the Bodhi plot to understand essentially how much could we increase the gain in the system, or how much could we be off in our estimate of the gain of the plant before the system goes unstable. Okay. So if we're looking at the frequency at which the magnitude or the phase crosses 180 degrees, that's equivalent to saying, what is the magnitude when the Nyquist plot crosses the negative real axis? Right, so negative real axis corresponds to negative 180 degrees or 180 degrees, however you want to look at it. So what we care about here is the crossing of the negative real axis. So let's come up with a different color. Right, so this is the point at which the Nyquist plot crosses the negative real axis. And we care about this distance, and this ends up being 1 over the gain margin. Okay, and this is basically saying that if we were to multiply the gain by the factor Gm, that would dilate this Nyquist plot to the point where this intersection exactly crosses at -1. All right. And so that is the factor at which we can multiply the gain and get marginal stability. All right. So this distance is 1 over Gm. And just note, this is not expressed in decibels. We'd have to convert to decibels. So oftentimes we see gain margin in terms of decibels. Yes? Okay, so if I were to, all right, so to take this, we have this, our starting point is this green line. That's our Nyquist plot, right? So this dimension here is just, say, a number. Say this distance here is 1/2, just for sake of argument. Right? If I were to now multiply this by a gain of 2, right, we're now going to have this intersection of the Nyquist plot and the negative real axis be exactly at the point -1. So the amount which I can increase the gain and get a marginal stability results is 2, right? But this position is at 1/2. 1 over GM is 1/2. Yeah. 0.
So then it's like you're at the critical location is your the one intangible and then K that for your function, like for your transfer function, like what you would change the gain to be.
So the gain margin is what could we change the gain to be before we get instability. Right. So it has nothing to do with what the gain actually is. The gain on the system is actually, if you look at the original transfer function, it's 4. So basically, if we were to start messing with our controller, how much could we increase the gain before the system goes unstable? Or you can alternatively think about this, how much can I be wrong in my estimate of the plant transfer function in terms of magnitude before the system goes unstable? Right, because your model of your plant's always going to be wrong.
What if it circles the real axis like crosses the real axis
The negative real axis? Yeah. Yeah. So we'll actually see that example. We'll go back to the handout that we just talked about, which has multiple crossings, and talk about that case. Yeah. So you have 2 gain margins in that case. Okay. So that's gain margin. Phase margin, if we look at this, this is the amount by which the phase of g of I omega exceeds negative 180 degrees at the frequency at which the magnitude is equal to 1. Right? Or we said the frequency at which the magnitude is equal to 1, we call that the crossover frequency. So, same idea. All right, so we said that crossover frequency, we've already labeled omega c. That's the frequency at which magnitude is equal to 1. All right, so we take this down. We say, all right, at what frequency does the phase plot cross that line? So, sorry, what is the phase at that frequency? And then how far away is that phase from negative 180? So that would be this dimension on a Bode plot. Okay. And then on the Nyquist plot, what we're doing is we're looking at when does the Nyquist plot cross the unit disk, because when it crosses the unit disk, that is when the magnitude is exactly equal to 1. And let me move something around really quick, because I drew this kind of in the way of a line I'm going to draw in a second. So what we do is we basically draw a construction line going from the origin to that intersection point. All right, it's not the color I wanted. There we go. All right, so I look at an intersection point, and then this intersection point, from this construction line, I can then draw this angle. Oops. Love it when it does that. All right, so if we look at this, okay, so we look at what is the frequency at which the magnitude crosses the unit disk. All right, we pick off that point at the Nyquist plot, and then that has a distance in terms of phase angle between that and negative 1. So this would be our phase margin for our system. Okay. Right. Any questions about that? Okay. So let's see some more examples. Let's go back to the handout. So, yeah, the handout would be more effective if I had this already drawn on it. Let's. All right. So this would be approximately unit disk. Note that the axes are not scaled perfectly here. Okay, so first example, what is the gain margin for the system? So 0, but I think you actually want to invert that, right? Infinity. Okay, so if we look at this distance, the distance at which this point crosses, and we're looking at the blue lines here, the first lines we started with, the distance at which this crosses the negative real axis, well, it never really does. So this distance is infinitesimal. And so we'll get gain margin being 1 over that. The gain margin for this particular example is infinity. So GM is equal to infinity. This happens quite often. So this happens whenever you have a Bode plot where the phase never crosses negative 180 degrees, right? The Bode plot never crosses negative 180. You can't pick off that point at which the frequency at which it crosses negative 180, right? So we say it has an infinite gain margin. So we would see this also on the root locus plot, that the root locus plot never goes into the right half plane, right? So we can just keep on increasing the gain to infinity and the system never goes unstable. Yes?
What if you assumed your system was like a simpler system like this, but it actually wasn't? Then you would think you'd have infinite gain, but theoretically you wouldn't because you didn't take into account for another parameter.
Exactly. Yeah. So that's why gain margin should not really be interpreted without phase margin together. So these are kind of dual notions. There's even more complicated margins that we won't get into this class that are probably a little bit more realistic, but the most basic ones are gain margin and phase margin. It's not uncommon to have infinite gain margin, but that should not be interpreted in terms of I can just crank up the gain to infinity. If we look at the phase margin in this case, it's definitely not infinity. Here. So if we look at the phase margin, we're taking this vector going from the origin out to this intersection point, and we would measure off this phase margin here. Okay, so this is a case of infinite gain margin, non-infinite phase margin. Okay.
Do we only measure gain margins from intersections with imaginary axis?
Negative real axis. Yeah, because we're worried about the case of the frequency at which the Bode plot or the Nyquist plot crosses negative 180. Just to follow on that point, we have a transfer function already loaded up here. So just to help with software tools, because I don't know if we'll get to the last two examples in the last 2 minutes. That may be reserved for Friday's class. Okay, so you may have seen some markings on the Bode plot portion of SISO tool that you didn't quite understand yet, and we'll explain that. Okay. So in this example, this was just an example of second order underdamped system with a pole at the origin. We haven't really talked about this Bode plot portion of SISO tool yet, but if we look, we see some markings that are put on this for us. So one, it says it's stable. The other thing is it gives you a GM of 6 decibels. All right, so this means a gain margin of 6 decibels. And what it's doing is it's marking this for you. So you see this is the intersection of your phase plot with negative 180. You go up in frequency, and you see a little line that draws from 0 dBs to the point at which this is at the frequency. So it'll mark the gain margin for you in SISO tool if you want to kind of play around this. And so the other one is that it looks at the point at which it crosses 0 decibels, and then it marks the phase margin. If I were to increase the gain on the system, well, one, I made the system unstable. Let me move this down just a little bit. Okay, so what did I just do? Okay, it still thinks I'm clicked. All right, that's the better way to do it. Okay, so you see it changed. Oh my God. I no longer clicked. All right, I'm just not going to touch anywhere in the plot. Okay, so you see that the crossover frequency changed because I changed the gain. It automatically marked that for you. So you see the phase margin is still around negative, or right around 90 degrees in this case. Gain margin is now considerably smaller because I've changed the magnitude. I've changed, yeah, basically I've changed the magnitude. So therefore, the phase hasn't changed by changing the gain, but I've changed this distance here. And so I can now increase the gain a little bit. You're going to now get negative gain margins and negative phase margins. That just means it's unstable. But these would be software tools you can kind of play around with and see these distances as well. So I went over, we'll do the last two examples in terms of gain margin and phase margin on the handout on Friday then, for that being really the last day of instruction. Right? All right, see you on Friday.